Hello everybody, and welcome back to another video on my channel. Today we will be talking about exponential and logarithmic derivatives and how to prove them. I've mentioned these in a few of my other videos where I just stated the formula, but I wanted to do this video to prove everything. And the reason I waited this long is because the proof requires the chain rule, but that's pretty much about it. So let's move on to the actual video. So our learning objective is to derive the derivative of e to the x and just any function to the power of x or any exponential function using the limit definition. Then it's to derive the derivative of the natural logarithm of x or any logarithm of x using the limit definition. Apply these derivatives and understand the relationship between exponential and logarithmic derivatives. Now, before we prove anything, let's quickly review the limit definition of the derivative. For any function f of x, the derivative is defined as this over here, f dash of x is equal to limit as h approaches 0 of f of x plus h minus f of x divided by h. And this will pretty much be our biggest tool in proving everything in this video. Now, the natural exponential function is e to the power of x, and key properties over here, I just included the value of e, but that will not be exactly necessary. Then the next one is a limit, which is very necessary, where you have limit as h approaches 0 of e to the h minus 1 divided by h is equal to 1. It's a very fundamental limit. And e to the power of a plus b is equal to e to the power of a times e to the power of b, which is just an exponential property in general. So the first thing is we need to use the limit definition. So e to the x plus h minus e to the x over h as limit as h approaches 0. Then using the exponential property, which was outlined above, we have e to the x times e to the h minus e to the x divided by h. Then all we have to do is factor out e to the x, and since its limit as h approaches 0, e to the x will not be affected, so we can bring it to the outside, or like say this multiplied by limit as h approaches 0 e to the h minus 1 divided by h, which is the fundamental limit we covered above, so that's equal to 1. So e to the x times 1 is equal to e to the x. So the derivative of e to the x is itself. And it's one of the few functions, or I think one of the only functions in my knowledge that actually does this. The natural logarithm function is going to be the next thing that we're going to prove. ln x is defined for x of greater than 0. Then the natural logarithm of e is equal to 1. Then we have e to the power of ln x is equal to x, inverse relationship, and a logarithm property, natural logarithm of ab is equal to natural logarithm of a plus natural logarithm of b. So let's start proving the derivative of the natural logarithm of x. So what we have to start is we first substitute ln x plus h minus ln x all divided by h. Then using logarithm properties, we have at h limit as h approaches 0, natural logarithm of x plus h divided by x over h is equal to limit as x approaches 0 of 1 plus h over x divided by 8. Next up, what we can do is we can do a little bit of substitution. So let's define a variable u, where u is equal to h over x plus, so h is equal to ux, and as h approaches 0, u will also approach 0. So we turn this from a derivative of h to a from a limit of h to a limit of u. So we have the limit as u approaches 0 of natural logarithm of 1 plus u over ux equal to 1 over x times limit u approaches 0 of the natural logarithm of 1 plus u divided by u. Then, using the fundamental limit above, where natural logarithm 1 plus u over u is equal to 1, that becomes 1 by x times 1 is equal to 1 by x, and that is the derivative of the natural logarithm of x. Now you might be like, wait, but where's the chain rule? Didn't you say at the beginning of the video that I waited because we needed to use the chain rule? And that is in fact correct. Even though you don't need the chain rule for this, for the general form of the exponential and logarithmic function derivatives, you will need this. Before we solve all of that, I think it's a better idea to do a few examples using the natural logarithm and the natural exponential. So the first problem is to find the derivative of f of x is equal to 3 times e to the power of x plus 2 times the natural logarithm of x. So what we need to do is first, of course, we'll say f dash of x is equal to then 3 times the derivative of e to the x. So 3 times d over dx of e to the x, then plus 2 times d over dx. Well, we really don't need all these brackets. So 2 times d over dx of natural logarithm. So then, after this, what happens is we just evaluate the rest of the derivatives. So the derivative of e to the power of x is e to the power of x itself, then plus 2 times the derivative of the natural logarithm of x. So that becomes 2 divided by x. And there you have it. Very simple problem, very simple solution, where we have 3 times e to the power of x plus 2 to the x as the solution. Now over here, using our derived formulas and applying it to the function also gives us the same answer. Now I'll say it again, and I've said it in previous videos. Where I'm talking over here and the sign I'm talking about over here is normally if you either finish the problem faster than I explained it, or maybe you pause the video and did it yourself. But also, so that's why the slide is there. But if you want, you can always listen to the explanations, as you might realize something that you didn't know earlier. Let's find the derivative of g of x is equal to x squared times e to the power of x. Now, we have the exponential derivative, but we also have the product rule since there's multiplication over here. So, what we can do is we can have g dash of x is equal to, I've already said the product rule in this previous video, so I won't say it down, but we can start by doing first the derivative of f of x times g of x, so 2x e to the x, then then we have plus f of x times the derivative of g of x, but that's still just to the power of x, as the derivative of e to the power of x is e to the power of x. And that is the derivative of our next function. 2x times e to the x plus x squared times e to the x. And over here we have the solution. This one I decided to simplify and factor, but I think it's honestly perfectly okay if you don't factor. There doesn't seem to be much unless your textbook or something says that, okay, no, you must have it simplified, or no, don't factor it at all and make it in its least factored form. And our final example for today is to find the derivative of h of x is equal to the natural logarithm of x cubed. Now, there are multiple ways to go about this, one without the chain rule and one with the chain rule. So I'll first start with the method that does not use the chain rule. So first we'll simplify h of x, then we'll figure out h dash of x. So h of x is equal to the natural logarithm of x cubed, or the natural logarithm of x times x times x. Now you can also do this another way, which I'll talk about shortly. Then using the logarithm property mentioned above, where you have if natural logarithm of a times b is equal to natural logarithm of AB is equal to the natural logarithm of A plus the natural logarithm of B. That also extends to multiple terms, so that will become ln x plus ln x plus ln. Then this becomes 3 times the natural logarithm of x. Another way you could have done it is using a different logarithm property, which states if we have the natural logarithm of x to the power of a, that's equal to a times the natural logarithm of x, and it'll pretty much produce this, it'll actually always produce the same result. Now using this, we can differentiate h of x. So dash of x, using the constant rule to pull 3 out of the equation, is going to be 3 divided by x. Now, as I said earlier, this is only one way to find the derivative. There are 2 ways, at least that I know of. And the second way is going to be using the chain rule. Now, what we need to do next is we keep the function as it is, but what we do is we say, okay, h dash of x, and then we use the chain rule. And the way we use the chain rule is, if you remember, the chain rule is the derivative of the outside function, so natural logarithm of u or whatever, then times the derivative of the inside function, which is x cubed. So h dash x is going to be equal to, first, the natural logarithm of u, where u is equal to x cubed, so 1 by u, so that'll be 1 by x cubed, then multiplied by the derivative of the inner function, which using the power rule is 3x squared. Then after simplifying, so x squared divided by x cubed is 1 by x, 3 times 1 is 3. So we'll also get the same answer, which is h dash of x is equal to 3 divided by x. And over here, we have using logarithm properties. Now we differentiate in the final answer, and this is just showing one method. Of course, using the chain rule would be, again, another method. Now we'll figure out how to prove general exponential functions using the derivative of e to the power of x, which was proved using the limit definition of the derivative above. So f of x is equal to a to the x, where a is greater than 0 and a is not equal to 1. So to find the derivative, we'll use the change of base formula. A to the x is equal to e times the natural logarithm of a times x. Now, this is not exactly the change of base formula, but it is what happens when we start simplifying and bringing the change of base formula into exponential form. This is the actual proof. Since we saw the change of base usage above, we have the derivative of a to the x is equal to the derivative of e to the natural logarithm of a times x. Then, using the chain rule where u is equal to ln a times x, we get e to the ln a times x, because e to the something is just the derivative of that. Then multiplied by ln a, because in this case a is a constant, so that's equal to a to the x times ln a. And that's the derivative of the base exponential function, like the basic or general exponential function. Now we're going to prove the general logarithmic function's derivative. So f of x is equal to log base a of x, where a is greater than 0 and a is not equal to 1, of course. Now this is what you might have seen earlier when I talked about the chain of base formula on my algebra series, which was a long time ago. But this is the more standard form of the change of base formula. But after you simplify it, it'll become the exponential form shown above. Now, what it says is logarithm base a of x is equal to natural logarithm of x divided by natural logarithm of a. Now this is the next step and pretty much the final slide in proving logarithm of base a of x is equal to 1 over x ln a. So what happens is d by dx of ln x over ln a, and since ln a is a constant, and that means 1 by ln a is a constant, we can move that out. So we have 1 over ln a times d by dx of ln x, is equal to 1 divided by ln a times 1 by x is equal to 1 by x ln a. Therefore, the derivative of the general logarithmic function is equal to 1 by x natural logarithm of a. Here are the key takeaways. These 4 formulas on the left are our essential formulas that you might need to memorize or just know how to prove. And our important limits: e to the power of h minus 1 divided by h is equal to 1. Limit as u approaches 0 of natural logarithm of 1 by u over u is equal to 1. And those are our limits that we'll need to know in order to prove this. And thank you so much for watching. I'm really happy that if any of you watched to the end, I really enjoyed that, and it really makes me appreciate what I've done. I hope that you learned something new from this video, and if you did and you like this style of content and you want to see more, please make sure to like, subscribe, and hit that notification button. It really means a lot to me, and that's really about it. But before you leave, please make sure to comment down below any encouragement, suggestions, or tips for the channel, or any questions you have. I'll be happy to answer them as long as they're not any personal questions. So thank you so much. See you in the next one, and bye-bye.